In this lecture, we discuss the possibility of generating hydrogen with the help of some of the advanced materials, some of which we have discussed earlier. So, the title of this lecture is Hydrogen Generation through MIEC Reactor. MIEC is nothing but mixed ionic and electronic conductivity in oxides. Okay. MIEC is conduction, actually mixed ionic and electronic conduction in oxides. Okay. And we make reactors out of that material. Let us discuss how exactly one can make hydrogen or separate hydrogen from a gas mixture using some of these oxides. Earlier we have discussed the conductivity or electrical conduction process in oxides under different conditions, partial pressure or different compositions, and we have encountered, we have come across some of them are purely ionic conductors, some of them are purely electronic conductor, either N type semiconductor or a P type semiconductor, and there is a group of oxides where this mixed oxides mixed conductivity is available. That means, partly it is ionic and partly it is electronic, and these oxides have a very useful role in generation of separation of hydrogen from a mixture of gas mixtures. Now, why hydrogen? We are in the basically we are talking about the energy sector, and hydrogen is one of the very useful, one can say, energy carrier, and it has a very high calorific value, and as well as it can be combined with oxygen to form water, and therefore, it can release a lot of energy. So, before we come to the actual discussion of how one can generate hydrogen using some of these mixed oxides, let me have a look at it or discuss the basically the energy sector. What is the problem of the energy sector and why we are so much interested in hydrogen or generating hydrogen. Earlier we have discussed about the fuel cell, that is one of the most efficient devices for converting hydrogen into electricity. Unfortunately, hydrogen is not available in nature. It is available in the combined form as water. We have huge resources of water, huge quantity of water available in this on this earth, surface of the earth, but we do not have hydrogen. On the other hand, hydrogen is a good energy carrier. Okay. It can, once available, it can be used as a very good fuel. However, the question is how to get hydrogen. So, it is completely related to energy and environment. Our interest of hydrogen is primarily from the environmental point of view. At the same time, it is a storehouse of energy, and that is why if you can use hydrogen as a source of energy, then at one go two of the things can be addressed or solved. One is the energy crisis and the other is the environmental problems or the environmental issues, because so far the fuels we use, most of the fuel we use for energy generation is fossil fuels, and once you burn the fossil fuel you generate carbon dioxide. You are invariably getting carbon dioxide is one of the products, and that carbon dioxide is polluting the environment. We have it is a very important greenhouse gas, and so global warming and all these things are happening primarily because we are burning so much of hydrocarbons and carbon dioxide is getting generated. The percentage of carbon dioxide in the environment in the Earth's atmosphere is increasing day by day. So, we have to go away from the carbon cycle, or the generation of carbon dioxide has to be minimized as much as possible. So, the whole sector is called the energy and environment sector, and what are the different strategies if you want to maintain our environment, and at the same energy, without energy we cannot live, we need energy, without energy the mankind cannot continue, the human race cannot continue like this. Therefore, we need to generate energy, but at the same time we have to keep our environment clean. So, what are the different strategies? General strategies are like this. We have to a long term strategy. There are long term strategy as well as short term strategy. In the sense long term, because we do not have the technology, we do not have the right kind of technology. We may have some ideas, but we do not have the technology to be pursued or to be commercial in a commercial scale. And therefore, one is a long term strategy, other will be a short term strategy. In the long term strategy, what we are doing is trying to do a complete changeover from the carbon economy to the hydrogen economy. That is the terminology normally used. That means basically from carbon cycle to hydrogen cycle. In carbon cycle, we are burning carbon or combining carbon with oxygen and producing carbon dioxide and carbon monoxide, both of which are pollutants so far the environment is concerned. So, if you can avoid that and still generate power or energy, the other alternative may be you go to the hydrogen economy. So, that you have a storehouse of hydrogen and generate hydrogen and then combine with oxygen to make it H2O. So, the product of combustion is H2O, which is a non-polluting gas or non-polluting species. Therefore, the ideal situation is, can we completely get rid of carbon and go to hydrogen, that is, but the question is how it can be economic, because hydrogen is not available as such. So, one has to generate hydrogen, and that generation of hydrogen also needs certain energy. Can we generate hydrogen without using any energy? It is not possible. So, you have to basically generate hydrogen with some energy, and then there is a trade offs where how exactly it can be done. Even if the technologies are available, they may not be commercially feasible. The success would however depend, if you want to completely change over to hydrogen, one would depend on the economic production of hydrogen or the efficient conversion of hydrogen to different forms of power, and it is not or, it is actually both. So, first of all you have to generate hydrogen, and then that hydrogen has to be converted to either electricity or some other motive powers in a much more efficient manner. Okay. Then you can conserve hydrogen also, conserve the fuel. So, this is our long term strategy, and people are working on various aspects of it, but the solutions are far away, still long time will take before we can solve these problems. Or of course, the other alternative which is already on, that is full dependence on renewable energy like solar energy, wind energy, wave energy and so on. Okay. So, we go to the renewable energy, and where you do not have to burn anything, you are not producing any gaseous product, either carbon dioxide, carbon monoxide or hydrogen or moisture, nothing is being produced. So, directly you are getting the energy from the solar or wind. However, once again they are also still quite costly, and although that technology is available and the technology is slowly being propagated and being used in more and more or extensive manner. So, in the short range time or till we get a complete solution of hydrogen energy, we can have a short range strategy or short term strategy, that is to reduce greenhouse gas emission by reduction in the consumption of the fossil fuel. That means, you consume less fossil fuel to generate the same amount of energy. So, that we need more efficient energy conversion devices compared to thermal power plants. We should have a much better efficient systems, so that we generate the same amount of power, but consuming less fuel. So, that is another strategy. Lot of work, lot of technological advancement are taking place in those areas. Or the use of fossil fuel to generate syngas, synthetic gas, which is basically a mixture of hydrogen, carbon monoxide and carbon dioxide, followed by an efficient separation of hydrogen and sequestration of carbon dioxide. That means, you can still use the fossil fuels, which is still we have some reserve in this world, and from that we convert that basically hydrocarbons to a mixture of hydrogen, carbon monoxide and carbon dioxide, and then separate out these three gases, because two of them hydrogen and carbon monoxide are combustible gases. One can generate power out of that, electrical power, and carbon dioxide can be sequestered. That means, you do not allow the carbon dioxide to the environment, but you can convert in various ways. There are many different techniques now available for sequestration. Means, you separate carbon dioxide and make it convert it into a solid form and put it in the earth, okay, or inside the earth. So that it does not go into the environment and pollute the environment. So, these are different strategies, different strategies being followed, and extensive research work is going on different aspects of what we have discussed just now. So, under this situation, hydrogen generation or hydrogen production is certainly a very important issue. How to get hydrogen by different techniques, so that we can slowly move towards the hydrogen economy. These are the different techniques by which one can make hydrogen. Simplest way or very one can think of, it is a very simple way to think that water can be electrolyzed. Water electrolysis is the most simplest way to get hydrogen, although it is not an economic. You actually need more power to electrolyze water than to generate power out of the hydrogen you produce. So, that is really a problem at this point of time. But if you can get power, electrical power from different sources like solar power, which is a renewable power. So, you are not producing any carbon you are not producing any environmental pollution, and therefore, you can generate, although it may not be a very efficient process, but at least you can get hydrogen using solar power. Still it is not an economic proposition. Or you can use nuclear power to electrolyze water. There are many different techniques, different methodology of water electrolysis, and one can have more efficient water electrolysis, not at room temperature, maybe at higher temperature with different kind of dopants, different kind of systems. Other possibility is still use fossil fuel, as I mentioned earlier, prepare syngas, synthetic gas, a mixture of different gases including hydrogen. This is basically one can do by so called a reforming reaction, and then separate out hydrogen. So, our interest is in the last one. If we have a syngas, generate syngas and then separate out hydrogen, and there some of the advanced ceramic oxides can be of help to us. So, the topic now will be the production and separation of hydrogen from hydrocarbon using a membrane reactor. Okay. Membrane reactor made of oxides. Basically, membrane is nothing but a semi-permeable barrier through which a selective species can move through and others are retained on the other side. Okay. So, that is the basic definition of membrane. So, it is called sometimes called the semi-permeable membranes, but the membrane structures may be different. Okay. The simplest way to imagine a membrane as having some porous structure. So, there may be pores of different sizes. So, depending on the size of the species, some of the species can go through and the others can be retained, just like a filter paper, okay, but at a much finer scale. So, this is basically a membrane or semi-permeable membrane. So, one can think of some porous membranes with controlled pore size, with redesigned pore size, but what we will be discussing today is not the porous membranes, basically a non-porous membranes. So, but even then one can drive some of the species through this dense structure, as we have done in case of fuel cell. Fuel cell is again the electrolyte is basically a dense membrane through which an oxygen can pass through, but no other gas can pass through. So, if you have an oxygen ion conductor, as in case of a zirconium yttrium stabilized zirconia, then oxygen can pass through the material. So, it is a kind of membrane through which only oxygen, particular species like oxygen can pass through, no other gas or no other species can pass through. So, it is also a membrane of that, and but it is a dense membrane, it is not a porous membrane. So, it is not a molecular diffusion, it is not a molecular diffusion, it is a ionic transport. So, a membrane having ionic transport property is basically a dense membrane. So, we will be discussing that and how such membranes can be used for the generation of hydrogen. Now, before that, before we come to the actually membrane or their characteristics and their properties, let us look at how one can get hydrogen from a hydrocarbon. Okay. There are various techniques, basically it is called reforming techniques, reforming reactions. There are three kind of reactions by which a hydrogen can be generated from hydrocarbon. One is called the steam reforming, the other is called partial oxidation, and the third one is called autothermal reforming. What are those characteristics or these details of these reactions? This is what we call the steam reforming. Reforming reaction is basically taking methane as one of the examples of hydrocarbon, CH4 plus H2O, CO plus H2, and this is a exothermic reaction. Okay. So, just by reaction with, of course, you need some catalysts and so on, we are not discussing that at this point of time, but the methane and H2O can generate carbon dioxide and hydrogen, which both of them has a combustible gases and then some energy associated with it. Water gas shift reaction is like this: carbon monoxide and H2O. This carbon monoxide and H2O can react to give you carbon dioxide and H2. The overall reaction of these addition of 2 is actually this is of course a endothermic reaction, and overall it is CH4 plus 2 H2O is CO2 plus 4 hydrogen. So, you are getting hydrogen here. So, mixture of carbon dioxide and hydrogen from the hydrocarbon, and that is what is known as the steam reforming reaction, and once again it is a exothermic reaction. In partial oxidation, the other type of reaction, reforming reaction, is partial oxidation reaction is CH4 again half O2 CO plus 2 H2, and this is a exothermic reaction, and a complete combustion. If you are taking up a complete combustion, then of course, it is much higher energy can be derived. So, that with oxygen, with full oxygen, full combustion, because here you are generating CO, here generating CO2. So, complete combustion is taking place 2 H2O, and you get a lot of energy here. The autothermal reforming, it is basically a combination of both steam reforming and partial oxidation, which have been just discussed. So, heat generated from the one is exothermic, another is endothermic, and therefore, partially you generate the heat, and that heat can be utilized for the reforming reaction. So, heat generated from the partial oxidation is used as an input to the for the steam reforming reaction. So, partially you burn it and generate some heat, and that heat can be used for the conversion of the hydrocarbon to the synthetic gas, that is H2 plus CO2. Now, if you have a semi-permeable membrane at this stage, so you are generating a steam, generating a mixture of gases, hydrogen and carbon dioxide, and if you have a material through which only hydrogen can pass through, but carbon dioxide is not passing through, then that can separate, that such a system can separate the hydrogen, and one can generate pure hydrogen out of that. So, carbon dioxide is separated. So, this is the role of semi-permeable membranes or the oxides which you are talking of. So, there can be not only oxides, so one can have polymers. These are this can also be used at a relatively low temperature, ceramics, inorganic membranes, that we will be discussing in a few minutes, and then we can also have cermets like a ceramic and metal composites. So, that can also be used for this purpose. Advantages of membrane reactors over conventional, well, these are reactors, this is a relatively new concept of using a reaction chamber and a separation chamber simultaneously. So, that is what the advantage is, that reduction in operation cost, higher conversion of hydrocarbons achieved, and simultaneous production and separation of the hydrogen. So, normally under the current situation, what happens is you reform the reaction gas and then take it to another chamber and try to find out, try to use either a membrane separation or different other separation techniques to separate the gases. So, the reaction chamber is different and the separation chamber is different, but if you can make a ceramic membrane either dense membrane or a porous membrane, but we are talking here about dense membrane. So, those dense membrane can form the reaction chamber itself, because this reaction takes higher temperature. So, the ceramics can be used as the reaction chamber, and the same ceramics, if it is a semi-permeable membrane, the property is there in that ceramics, that can also be used as a separation chamber. So, what ultimately at the end of the process you will get a pure hydrogen after the reaction and separation is complete within the same chamber. So, these are the advantages when you get compared to the normal tubular reactors which had been standardized over the decades for the reforming reactions. Well, these are some of the characteristics of the inorganic membranes we are talking of. High selectivity for separation, the separation efficiency is very high, operate at temperatures, because these are inorganic membranes or ceramic membranes can operate at a temperature of 500 to 1000 degrees centigrade, which is also a high temperature required for the reforming reaction. Resistance to corrosive liquids and gases, they are relatively inert and therefore, they are less corrosive or no corrosion at all. Can withstand high pressure, because the mechanical strength of these membranes compared to, of course, while we are talking at this point is basically we are talking about comparison with polymers. So, this is MIEC. In this context, we have an importance of the MIEC, and that is mixed ionic and electronic conductor. Okay. So, this is the basic discussion which we are coming to. Two different forms of MIEC. One is, or types you can say, one is oxygen ion plus electronic conductor, and the other is proton or hydrogen ion conductor and electronic conductor. We have come across oxygen ion conductivity in YSZ, which is of course a pure ionic conductor, there is no electronic conductivity, but there are some other oxides, mixed oxides, perovskite based, we will see what are those, in which we have oxygen ion conductivity, mixed ion conductivity, oxygen ion conductivity in addition to electronic conductivity. So, in the same material we have both. Similarly, there are another group of materials in which not the oxygen ion, but the hydrogen ion is the conductor. We have come across earlier in a proton membrane electrolyte or the polymer electrolyte fuel cell, where hydrogen ion is the conducting species in a polymer matrix. Okay. So, the polymer is hydrogen ion conductor. Similar things can happen in some of the oxides, but it is not pure hydrogen ion conductor, it is partly hydrogen ion conductivity and partly electronic conductivity. So, that can also be used for this kind of separation. Well, first of all, let us take, if we have a oxygen ion conductor or a mixed conductor, oxygen ion plus electronic conductor, this, as I mentioned few minutes back, that we are talking about a reaction chamber where actually it is a membrane and reaction taking place simultaneously, and the membrane is basically allowing certain species to pass through and allowing the reaction to proceed in a certain direction. So, this is an example where oxygen and electron both are the conducting species. So, this is our membrane and the wall of the reactor, you can say. So, you have the oxygen ion conduction and electron conduction. So, oxygen ion is moving in this direction and electron will be moving in the opposite direction. Okay. So, this is the normal situation, ion will move in one direction and electron will move in the other direction. So, particularly for the oxygen ion. Now, this is some sort of a electrolytic electrolyte. Okay. Earlier we have seen a fuel cell where ion is moving, oxygen ion moving through the electrolyte and electron is moving in the outer circuit. Okay. Electron is moving in the outer circuit generating the current, and you can draw current because of the flow of oxygen ion. Here there is no question of outer circuit, okay. There is no EMF generating, we are not impressing any voltage also from outside. What we are having is basically a potential difference, oxygen potential difference, and on one side high oxygen potential, on the other side low oxygen potential, and that is the driving force. That is the driving force which drives oxygen ion to move from one side to the other. But since an oxygen ion is moving, okay, so there will be a charge accumulation on one side. So, from one side it will be ionized and goes to the other side. So, there will be charge accumulation until and unless there is a neutralization. So, the electron has to come back. In case of fuel cell, the electron was moving in the outer circuit. So, you are getting a current in the external circuit. Here it is basically a kind of short circuiting. The electron is moving within the material itself. So, this negative charge in the form of sitting over oxygen ion, this electronic charge is moving in this direction, but a corresponding electronic charge has to also move in the form of electrons. So, this is in the form of ions and this is in the form of electrons, and that is how the circuit is completed. Okay. So, there is no EMF generated, there is no impressed EMF from outside. So, on its own the charge is getting transported through the material, and the driving force is basically oxygen potential, higher oxygen potential on the other side and lower oxygen potential on the higher oxygen potential on one side and the lower oxygen potential on the other side. Now, one can imagine what kind of reforming hydrocarbons can take place. Once again, taking an example of CH4 as the hydrocarbon. On this side hydrocarbon is flowing, and once it comes in contact with this at a relatively high temperature, there will be some catalyst may be required for its ionization and so on. So, CH4 will be reacting with the oxygen ion which is coming from the other side. This oxygen ion will come and react with this and forming carbon monoxide and hydrogen. So, it is basically a dissociation of this in the or a oxidation of this actually, not the oxidation of CH4 and forming CO plus H2 and releasing 2 electrons. Now, these electrons will be transported back to this system. Okay. This will come to this and then combine with this, and on the other hand this side the reaction will be oxygen which is coming from air. So, oxygen is flowing and oxygen is getting consumed by this reaction. These electrons which is coming from the other side is ionizing this gas and becoming an oxygen ion. So, by this process it will continue. Okay. So, on one side you have a hydrocarbon and other side is a flow of air, and automatically the product is a mixture of carbon monoxide and hydrogen. Okay. So, this is the reforming reaction using this kind of a mixed ionic electronic conductor. One can also get similar situations. Okay. This is a separation, a separation, not the reforming reaction. In the reforming reaction we have already got the carbon monoxide and hydrogen, and in this reactor we are getting separating them. We have a feed which is carbon dioxide, carbon monoxide and hydrogen, and then this material is hydrogen ion conductor and together with the electronic conductivity. So, you have a hydrogen ion conductivity as well as electronic, unlike the previous one which is oxygen ion conductivity and electronic conductivity. Here the material is hydrogen ion conductor together with electronic conductor, and if so both of them will move in the same direction because one is positive another is negative. So, both of them will move in the same direction. Here carbon monoxide hydrogen will be separated out or be ionized with H plus and 2 electron, and this hydrogen will move through this. Okay. So, here this electron hydrogen this will be 2 this will be positive, this will be 2 H, not 2 minus, but it will be 2 H plus. 2 H plus and 2 electron will make hydrogen. Okay. So, let me change that and let me correct that. Right. Okay. So, 2H plus 2 electron, that will make H2. Okay. So, this hydrogen actually be available on the other side and carbon monoxide will go through. Okay. So, it can be, we have taken carbon monoxide here, but it can be a mixture of carbon dioxide and hydrogen as well. Okay. So, to maintain the similarity, we have kept this carbon monoxide and hydrogen, the syngas, but it can have carbon dioxide and hydrogen. So, carbon dioxide will come here and hydrogen will go on the other side. So, you can get hydrogen on the other side after the reforming reaction of the hydrocarbon. So, by the process of two things, this can be done in the same chamber also, and if you have a reform gas, you can separate it from this using a MIEC membrane, the dense, so called dense membrane. Well, there are using an hydrogen ion conductor, also one can make some kind of an oxidation reaction like this. CH4 in fact, it is what we call oligomerization of methane to ethane. Okay. So, they are taking oxygen from this side, one can CH4 can be converted to C2H4 by this reaction. The same process is same. So, CH4 plus becomes C2H4 plus 4 hydrogen and then 4 electrons here, these 4 electrons goes there, hydrogen also goes in the same direction, and it combines there with H2O formation with air, oxygen from taking oxygen from the air. So, nitrogen and oxygen and ultimately nitrogen and H2O. Okay. So, these kind of membranes or membrane reactors can be used for making different chemical reactions, particularly in the gaseous phase, and both mixed oxides, either hydrogen electron or oxygen electron can be used for this kind of carrying out such kind of reactions at an elevated temperature. The actual materials, we have seen that some of them are oxygen ion conductor together with electron conductor, and others are hydrogen ion conductors together with electronic conductor. The materials, actual materials which have been found or have been shown such properties, the materials of current interest is this one. There may be few others, but this is one of them, important one out of them. It is lanthanum, strontium, iron, cobalt ferrite actually. Okay. So, this is actually a LSCF, one can say. Lanthanum, strontium is again a perovskite structure, basically a distorted kind of perovskite structure, and you have this compound. Okay. So, this is what they call the oxygen for oxygen separation, oxygen ion plus electronic conductivity. Some of the new materials are also being researched on, that is lanthanum, strontium, gallium ferrite. Instead of cobalt, it use gallium, or even CO2 lanthanum chromite. Lanthanum chromite you have come across as a interconnect material, and a CO2 a mixture is basically a composite of CO2 and lanthanum chromite, that can also be used for these purposes. The advantages of this kind of material, high selectivity of oxygen under very low pressure, 10 to the minus 3 bar. Basically, it is the partial pressure of oxygen which is the driving force, either the partial pressure of oxygen or partial pressure of hydrogen, that is the basic driving force to make the reaction happen in one direction, operates under very high partial pressure gradient. So, even under very high partial pressure gradient, they do not change their structure. So, they do not change their properties also. High yield of oxygen collection. So, one can have you can separate oxygen by this process. Materials for the hydrogen separation is like this, is strontium cerate, once again a perovskite compound having proton conductivity. What is called the hydrogen separation is basically a proton conductor, hydrogen ion conductor, that was oxygen ion conductor. Barium jaconate is another compound, and few of the other relatively new materials which have been researched on is lanthanum niobate, strontium titanate and strontium titanium oxide. This is also another form of strontium titanate of a different molecular ratio. Advantages again the similar things, stable at carbon dioxide atmosphere and high proton conductivity. Okay. So, some of the oxides, as you can see, do also have proton conductivity, and not only oxygen ion conductivity, one can have hydrogen ion conductivity in such materials. Well, these are some of the comparison of some of the membranes hydrogen for hydrogen, particularly for hydrogen separation. We have dense polymer membrane where there is a proton conductivity. So, we have seen like Nafion, these are operated at a lower temperature. However, the selectivity, hydrogen ion selectivity is relatively low, and these are polymer materials, basically polymer materials, dense polymers. Microporous ceramics, these are well, there are we will discuss separately what are the microporous ceramics and what are the porous membranes, inorganic membranes or ceramic membranes. They have, in addition to the gas separation, they have many other applications. We will have different lectures, separate lectures on them. So, microporous ceramics is another group. Then dense metallic material, palladium and its alloys, this is also dense material, and these can be used for hydrogen separation. Maybe we will discuss separately. Not they are not mixed ion conductors, but some of these palladium and its alloys actually can absorb lot of hydrogen, and that is how they can separate hydrogen from a mixture of hydrogen and carbon dioxide or carbon monoxide or synthetic gases. So, this is a useful material, but the mechanism of separation is a little different. Okay. And you can see the selectivity is very high, more than 1000. So, the ratio is more than 1000, how much is retained and how much goes to the other side. And porous carbon can also be used, but the selectivity is again very low, but it can be used at a very high temperature. What we have discussed so far is actually the proton conducting ceramics, and you can see compared to others the selectivity or the separation efficiency is extremely high. Once again, it is comparable to the dense metallic membranes of palladium. As you can see, palladium is quite costly material. Compared to that, these are quite cheaper material, and one can have more or less a comparable selectivity in this kind of membranes, and they can also operate at a fairly high temperature. So, these are some of the comparisons of membranes, particularly for hydrogen separation. Well, in the last slide in this is basically it is not the dense membrane only which can be used for hydrogen separation, but there are porous membranes. Porous membranes, again high temperature membranes, can also be used for hydrogen separation. We have in an earlier slide we have talked about the microporous ceramic membranes, right. Here the microporous, these are all dense membranes, it is made of polymer, this is made of metal, this is porous carbon membrane and this is dense ceramic membrane. So, we have already discussed them, dense membrane as a polymer membranes we have discussed in some other context. Metallic membrane we have not been we did not discuss, but as I just mentioned that it can be used in a different way because palladium has a lot of adsorption property towards hydrogen. But these are two, one is porous carbon and microporous ceramics can also be used for hydrogen separation, and as you can see the zeolites. Okay. The zeolites they are made of they can be made of silica, alumina, zirconia, not all for hydrogen separation, they can be used for many different other purposes, but particularly these zeolites, membranes made of zeolites can be used for hydrogen separation. How? That is given in the next slide. Because it controls the pore size, the molecular sieves and the pore size of molecular sieves and the kinetic diameter of the gas molecules, that is what is compared here. These are the pore size dimensions in the in units of angstroms. So, it is 5 angstroms, 10 angstroms and 15 angstroms, and on this side there are different compounds, ceramic compounds, and most of them are zeolites. Now, zeolites they are basically silicate, different kind of silicates, and their structures is very interesting. Most of the zeolites has some kind of a molecular passage or a molecular hole through which some of these oxides, some of these species can pass through. So, these are not the pores are not made out of the agglomeration of the powders. Okay. As we know, ceramics are porous materials because they are basically prepared from fine powders, and when these fine powders gets consolidated, you have always some pores generated. Okay. So, these are basically physical pores. Now, zeolites also has some pores, but in a different structure, a different scale. They are crystallographic pores. In the atoms of these zeolites or the ions in the zeolites in such a manner or arranged in such a manner, there are crystallographic passages, crystallographic tunnels. So, these tunnels are good enough, in fact, it is through and through tunnels, and so these are generated not because of the agglomeration of the powders or consolidation of the powders, but because of the crystallographic arrangement of the atoms. Okay. So, the atoms are arranged in such a way, there are some crystallographic tunnels, and these tunnel sizes differ depending on the particular composition. So, these are different kind of compositions and different kind of structures where the tunnel size are different, and it starts from, as you can see here, about 2.5 angstrom, and one can go up to 10 angstroms. So, for example, aluminum phosphate has about a very high more than very close to 10 angstrom size. Zeolite X, these are some standard some standard compositions which have been categorized, been named as zeolite X, ZSN 5, zeolite A and sodalite. All of them are zeolites of different compositions and different slightly different structures, and therefore, they have different pore sizes or crystallographic pore sizes or tunnel sizes. And on this other side, on the right hand side, you have the kinetic diameter of some of the gaseous molecules. Okay. You have water molecule is here, then you have H2, CO2, methane, propane, isobutane and SF6, benzene and so on. So, depending on the particular composition of these or the particular molecules, they have different kinetic diameter of the molecules. So, they also vary to some extent. So, if you have a particular for example, sodalite, sodalite, the tunnel size, the crystallographic tunnel size is somewhere here in between hydrogen and carbon dioxide, just very closely precisely below the carbon dioxide and just above the H2O. So, if you can make synthesize zeolite like sodalite, then you can actually retain hydrogen, you can pass through hydrogen, because this diameter is more than that of hydrogen. So, you can pass through hydrogen and retain carbon dioxide. So, that is also one of the principles by which, using the pore size, very definite pore size from the crystallographic structures, one can separate hydrogen from carbon dioxide. So, such membranes are also being developed, and it has been tried out in different research labs throughout the world, that membranes of this kind, the molecular based on molecular sieves. Of course, zeolites have been used as a molecular sieve for a long time for adsorption of different gases and catalysis, catalyst carriers and so on. So, zeolites have been in use, have been synthesized, many of the different kind of zeolites have been used in context of the catalysts. Okay. So, that is the reason they have been given different kind of names, depending on their particular characteristics. So, what we are interested here is to find out a pore size of a particular zeolite whose pore size is slightly larger than hydrogen and smaller than CO2. Or so, if one can use them just by a molecular diffusion, not by an ionic diffusion. Earlier what we have discussed is the ionic diffusion, here we are talking about the molecular diffusion. By that process one can actually separate out hydrogen and carbon dioxide. So, this is another technique by using porous membranes. So, we have discussed both the dense membranes, where you have mixed ionic and electronic conductivity, and there are porous membranes. By controlling the crystal structure, you can maintain a particular pore size, a very definite pore size, which is in between hydrogen and carbon dioxide, one can separate them out. So, first of all you have to have, so basically what we are talking about is, first of all try to get a mixture of gases, the hydrogen and carbon dioxide, from hydrocarbons, the available hydrocarbons, and then separate hydrogen and carbon dioxide. So, carbon dioxide of course should not be released to the atmosphere, so that it does not increase the pollution, but hydrogen can be used for as a fuel to generate electricity or other forms of energy. So, this is the basic philosophy on which some of the advanced ceramic materials are also being used in the area of energy technology. So, to conclude, we have earlier discussed the fuel cell in the domain of energy technology, where hydrogen is one of the basic fuels, but then since hydrogen is not available naturally, we have to generate hydrogen by some means, and one of the ways is to is a source of your hydrocarbon, which can be reformed to prepare a synthetic gas and then generate hydrogen. And other of course is to use renewable energy and electrolyze water. So, those are most of these processes are still not commercially being tried out, but experimentally the technology is getting developed. So, that is all so far as the energy technology and the application of advanced materials, advanced ceramics in the sector of in the energy sector is concerned. Thank you for your attention.